Bismillahirrahmanirrahim. Today, inshallah, we'll talk about the last of the four important segments or lines of a triangle, the altitude. We have already spoken about the perpendicular bisectors, and we said that they were concurrent, and the point of their concurrency was the circumcenter. We have already spoken about the angle bisectors and how the point of concurrency was the incenter, and we had also spoken about the medians and how their point of concurrency was called the centroid, and that was the center of mass of the triangle, so to speak. Today, inshallah, we shall talk about the altitude and their point of concurrency, which is named the orthocenter. The term ortho is another name for perpendicular. Sometimes, if you get tired of saying the lines are perpendicular, you can say the lines are orthogonal, and that would mean the same. Now, an altitude is a line that starts from one of the vertices. As we have said before, altitude starts at one of the vertex and goes to the opposite side and is perpendicular to the opposite side. So it starts here and it goes here to this side and it is perpendicular to this side. Okay, so the altitude is a line that starts at a vertex of a triangle and is perpendicular to the opposite side. Now, if we were to draw the altitudes of this particular triangle that I've drawn, triangle ABC, they would look like this. First altitude, okay, from here to here. Now, you're probably familiar with the altitude because we have used them to calculate the area of a triangle. And the formula for the area of a triangle, if you recall, was 1/2 the base times the height. And the height, in fact, is the altitude. Now, any of the sides of a triangle can act as a base. So the base could be this could be this, or this could be this. But the height then would have to be the corresponding altitude. In other words, if you're using AB as the base of the triangle to calculate the area, you would have to use this H here as the height of the triangle. On the other hand, if you wanted to use this segment AB as the base of the triangle, then you would have to use the corresponding height, the height that corresponds to that side, which is this segment over here. And finally, if you wanted to use this side BC, as the base of the triangle to calculate the area, you would have to use the corresponding height, which is over here. Now again, as you can see, as I've drawn these, the three altitudes are concurrent. The point of concurrency of the altitude, again, is called the orthocenter. So again, you're probably familiar with the altitudes because that's what we use to calculate the areas of triangles. Now, sometimes students have some difficulty finding these altitudes of triangles, so I thought we'd do a little bit of exercise. Now, let's say I have this triangle DEF, and I wanted to calculate its area. Then we know that the area of a triangle is 1/2 the base times height. Now, let's say I wanted to use DF as the base. Now, the height would be corresponding altitude from the vertex E to this side. But the altitude has to be perpendicular like this, okay? But this segment DF, does not extend, that side of the triangle does not extend beyond this over here. So what you would have to do is you kind of have to extend this side a little bit like this, okay? And then you can draw the altitude of this triangle from side E like this and going over there like thus. So the altitude for DF, the one that corresponds with DF, starts from this side over here. So the altitude again is the line that's from this vertex to this side, but that has to be perpendicular to it. So in this case, it would be perpendicular to it like this. So the altitude here lies outside the triangle. Okay? Now, if you wanted to use DE as the side to calculate the area of this particular triangle, so let's say this side is 6, you would have to find the altitude that corresponds to this side from here to here. Well, the altitude again is from the opposite side, from F, and is perpendicular to this side. Then the altitude would be like this, and that would be the altitude, whatever the height of this segment is. So for an obtuse triangle like this, the altitude is on the outside of the triangle. For an acute triangle like this, the altitude is on the inside. For an obtuse triangle, the altitude, in fact, is on the outside. Now I'm going to draw the three altitudes here for this obtuse triangle, and you will see that the orthocenter is, in fact, on the outside of the triangle. Orthocenter, of course, is the point of concurrency of the altitudes. So here's the first altitude over here, like this, and I shall draw the second altitude over here from this side that's perpendicular to this. Now I'm doing this. Now you have to understand I'm doing that because I know I'm extending this line like this, and this would be perpendicular like that. Okay, and finally the third side, the altitude again. If I would have to extend this segment a little bit like this, okay, and then I would have to draw the altitude from that side, and it would be like something like this. Ta-da! And then these would be perpendicular once you extend that. So the three altitudes again are concurrent, and the point of concurrency for the altitudes here is over here, and that is the orthocenter. So that is the orthocenter of an obtuse triangle. For an acute triangle, the orthocenter was inside the triangle, and for an obtuse triangle, the orthocenter is on the outside of the triangle. And for a right triangle, as you can imagine, the orthocenter is, that's reasonably easy enough to figure out. Watch this. I will just draw a right triangle for you like this. Now the altitude is a line that goes from the vertex to the opposite side. In this case, it would be from here to this side, and that's perpendicular, and from here is this side, and that's perpendicular like this, and that is that vertex right there, and that is the orthocenter of a right triangle. Now we have talked about the perpendicular bisectors, how they were special in that they gave us the circumcenter, and we talked about the angle bisectors, how they were special, that they gave us the incenter, and the medians, how they were special, that they gave us the centroid. And you probably say, okay, so what's special about the orthocenter? Well, the orthocenter is the height of the triangle. It is that segment which allows us to find the area of the triangle. There are many other special properties of the orthocenter. One that we shall explore in the future, inshallah, and that it is the most important line or segment that is associated with the famous 9-point circle. Inshallah, we'll talk about the 9-point circle in the future. Until then, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.